Hi, welcome back. Today we have a question which is consider the symmetrical flow of air around the cylinder. As you can see there, the control volume excluding the cylinder is shown in figure below. The velocity distribution downstream here of the cylinder is approximated with the parabola as shown. Determine the drag force per meters of length acting on the cylinder. Use rho, which is density equal to 1.23 kilogram per meter cubic. So first, we need to analyze what the question asks. So determine the drag force per meter of length. So this is the drag force. Because of the flow, it will create the drag force. So the first step, what we're gonna do is we must analyze the flow. First, the flow coming from the left to the right, from A, B, and go to CD surface. So we must realize that this is open, all right, and we have the cylinder at the middle of this area. Thus, the flow is not going in one direction, only at the CD point area. So it will cross the surface of BC and AD as well. So we have 3 outlets and 1 inlet here. Right? So this is the flow. The first step that we're gonna do is that we need to apply the Renault transport theorem for the momentum equation. Remember our Renault transport theorem RTT, where step number 1 start with applying the momentum equation using the Renault transport theorem formula. Alright, so we need to apply momentum equation. Alright, using Renault transport theorem. Alright, so based on the Renault transport theorem, let's state here our Renault transport theorem, which is summations of force. This is for momentum equal to total D over dt. Alright, this is an extensive property of the system. Alright, the Renault number start from here is equal to small d over dt. This is into the control volume. Integrations of control volume. Intensive property. Rho dV. This is a volume. Alright. Plus integrations of control surface. Remember that when we involve of RTT, we have 2 components, control volume and control surface. So here you see the imaginary line. This is the control surface. Inside it is the control volume. That's why we have 2 terms here, control volume and control surface. However, for the control surface, we use the flux term or the flow cross the surface area. So this is as well the intensive property cross the surface area multiplied with rho V dot product and normal to the surface area dA. Alright. So for this case, we apply momentum. Momentum is mass time velocity. Alright. So the extensive property here is momentum. How to get the intensive property so that we can apply in this RTT equation? So intensive property is equal to capital N extensive property divided with mass. So N is mass time velocity over mass. We cancel mass, we got the velocity. So we can actually replace here with velocity and velocity. Now we look at the question. Alright, we assume that the flow is under steady state flow. Alright, there is no change of property over time. So we can cancel out this term over time, dt and dt as well. So we only left summation of forces because this relate to the momentum equal to only this term, integration of control surface, which is intensive property replaced with velocity rho v dot n dA. Alright. In other words, we can actually replace Vn is the velocity perpendicular to the cross-sectional area. So Vn is V. V multiplied with V is V the power of 2. So control surface, integration of control surface. Alright. We can say rho V squared dA. Now we have simplified the RTT equation, which is summation of force that focused on the flux equal to integration of control surface rho v squared dA. And then we need to analyze. We have how many surface involved in the flow? We have A, B, B, C, C, D, and dA. We have to include all the surfaces here. And step number 2. Right? Apply for all the surface involved. So the surface involved is, let's say we start with CD first. Alright? You can start with any surface. For my choice, I try to start with CD because this involves of the formula, the parabolic CD. Okay? So before we start to look at here, we must know the summation of force. What is the force related in this flow? Only the drag force, which is pointed to the left. When the force pointed to the left, it is negative force. So we include here negative F because going to the left. Alright. This notation should be left is negative and right is positive. When it is counter, it is negative. So in this case, negative F equal to, right, integration of area, surface area, which is we cover first the CD. Area of CD. Okay. Again, rho V squared dA plus integrations of AD, A to D. Area cross-sectional area AD. Same again, rho V squared dA. Okay. And then after AD, we look at BC because AD is symmetrical with BC. Plus area BC rho V squared dA. And then lastly is AB. You notice that when the flux, this is the rule of flux. Yeah. When the flux entering the control volume, it is negative. When it is out from control volume, it is positive. Now in this case, entering the CB, control volume, it is negative. So here you notice this is positive because it is out from control volume. And then here in this case it is negative because into the control volume. Integration of area, which is area AB, rho V squared dA. This is the most important form of Renault transport theorem apply to this case. Okay. Alright, we notice that AD and BC have the steady of velocity U infinity, which is the constant velocity across the surface area. So it is given that it is 30 meter per second. And we can actually simplify the flux of AD and BC here. AD and BC here. We notice that this term, the velocity is constant. Alright, which is 30 meter per second. And the density here, okay, the density of air and the surface area. Okay. So from this case, okay, we need to know the mass flow rate because we don't have the cross-sectional area here. If we know this length and then we know the width of this, we can get the dA. And then we can straight away substitute in this equation. However, for this case, we don't have the dA. And we can use alternatively the other equation of, you notice that this one, when we expand further, this is rho V A multiply with V. Yes, this is B squared, this is B, V 2 times. Rho VA is actually same with mass flow rate. This is the continuity equations of the mass flow rate. Alright, m dot is equal to rho VA. So this term we can replace with m dot V AD, and this term as well, the symmetrical, we can replace with m dot V BC. Velocity AD and BC, we know it is 30 meter per second because it is given here. The velocity cross the AD and BC 30 meter per second. Thus, in this case, okay, we can simplify further. Summation of force, which is negative F, equal to integration of area CD, which is C to D here. Alright, C to D given with the equation of velocity with the function of y, uy equal to 29 plus y squared over 100. And look at here. It is given that from the center until to the top is 10 meter. So it starts with 0 here as the reference. So we shall integrate from 0 to 10 meter. How about the other side? We have to multiply by 2 to ease our calculation. So we can do the integrations. Alright, from here to here. From 0 to 10. And we must multiply with 2 to cover the bottom side. So in this case, 2 times integrations of from 0 to 10 that I mentioned before. We do from the center to the top and multiply with 2 to get the bottom as well, because this is symmetrical. Alright, and then replace with rho. Rho is rho, we know already, and velocity given here is u. So just substitute all this value, 29. If you want to substitute, please make a bracket. 29 plus y squared over 100 bracket squared, because this is v squared. And here is refer to function of y. Alright, this is definitely in term of y, and this is replaced with dy. This dy is the length. Remember that the question asks drag force per meter. That means this velocity per meter. So when the dy multiply with meter, we will get the area. That's why this is dy. Alright, this is per meter. So when we multiply with meter, we will get this is area. Okay, and then plus this one. The term MV and MV with AD and BC is the same, symmetrical. We can simplify to make it 2 times. 2 times mass flow rate. Let's say we focus on BC. Mass flow rate BC, V, BC. Because this is the same, symmetrical. And this part, AB, we look at AB, which is negative into the system. And the given velocity here is 30 as well. Alright, so just replace here negative. Rho is 1.23, because all this term is constant. We can replace directly. Multiply with velocity, which is 30 squared dA. Area given here is AB area is 10 plus 10, 20. Because this is per meter. That means we multiply with 1 per meter. So 20 only. Okay, per meter, remember? So multiply with 20. Alright, per meter. This is actually multiply with 1. Because per meter. It is the same thing. So from here, we can simplify negative f equal to 2. Okay, integration of 0 to 10. Rho is 1.23. This one, 29 plus y squared over 100 squared. Remember, dy is actually also multiplied with 1 because per meter. Okay, like this one. Dy plus 2. Okay, 2m dot bc vbc. Okay, and then you can actually solve this using calculator. Okay, 1.23 multiply with 30 squared multiply with 20, you will get minus 22140. Okay, so we notice that this term we have how many unknown? We have force that definitely that we're gonna get at the end of this question, and we have velocity BC given, which is 30, we can replace, but only this term, the mass flow rate of BC. So what to do here? Step number 3, we need to find M mass flow rate of BC. So mass flow rate of BC. Okay, step number 3. We need to apply continuity equation. Continuity equation in terms of Renault transport theorem. So what's the Renault transport theorem? Which is capital D over dt n of the system. This is extensive property equal to d small d over dt integration of control volume intensive property rho dv. This is volume plus integration of control surface intensive property, alright, rho v dot n, this is normal to the surface area dA. Consider this is under steady state. We remove anything related to time. So we can cancel this 0 and cancel this 0. So in this case, we left only 0 equal to integration of control surface intensive property. What is the intensive property for continuity? Remember that continuity is for mass. So extensive property for continuity is mass. In order to get the intensive property, which is n over mass. So mass divide with mass, you will get 1. So replace with intensive property equal to 1. Definitely you will get rho v dot n product dA. Okay. So from here, let's apply to all the flux across the surface area AB, BC, CD, and DA. So we can start with any surface area. In this case, I try to start with AD first. Okay. So from here, step number 4. Okay, we go to step number 4. Apply to all surfaces area or surface or area. So in this case, we can apply to 0 is 0 equal to integrations of area. Okay, AD rho v dot n dA. This is positive because out of control volume plus integration of area BC rho v dot n dA. Okay, plus integrations of area, which is area CD rho v dot n dA, and lastly is AB, which is into the control volume. Thus, in this case, we need to minus A, B, rho V dot N dA. Alright. So for this case, AD and BC. Where is the AD? AD and BC is symmetrical. And we know that rho VA, this is rho V and A. This term is equal to mass flow rate. And rho VA, because N is the unity, alright, unit vector. Rho VA is mass flow rate. Mass flow rate of AD is equal to BC. So now we can replace with mass flow rate of AD plus mass flow rate of BC. Later on we can simplify. We focus on BC. We multiply with 2 plus integration of area CD. So this is CD. Given here the velocity. So we can straight away apply, because this is focus on from velocity from 0 to 10, we can multiply with 2 to get the bottom side. So CD is 2 times integration from 0 to 10. Rho velocity, we shall replace with velocity, which is 29 plus y squared over 100. This is definitely dy, because multiply with 1, we got area. Okay, and then this one just minus. Rho is, this is constant, AB is constant. You can see here the flow is constant. So just substitute the value. Okay, so rho is 1.23. Multiply with velocity is 30, and the area, cross-sectional area is 20. Okay, because you look at here, this is 10 plus 10, 20. Multiply with 1 per meter. Alright, per meter or per 1 meter. So from here, is 20. So let's simplify further this equation. 0 equal to 2 times, because this is symmetry, 2 times mass flow rate of BC that we are looking before this. Once we found the mass flow rate of BC, we can substitute into this equation, mass flow rate of BC. And then this one, 2 plus 2 rho is 1.23. Okay, this one we can directly integrate. Okay, we can integrate here. 29 integrate with dy, we get 29y plus y squared is y cubed plus 1 over 3 multiply with 100 is 300. From 0 to 10, this is limit integral. Minus with, we solve this using calculator, definitely you will get 738. Okay, so for this case, try to solve using your calculator. You will get 0 to mass flow rate of BC. Okay, this one plus 2. This one you solve. 2 multiplied with 1.23, you will get 2.46. This one you solve, you substitute with 10. Definitely you will get 293.33 minus 738. Okay. And lastly, finally, you will get M flow rate of BC is equal to 8.2 kilogram per second per meter. Okay. So for this case, mass flow rate of BC, you can replace with the step number 2, which is mass flow rate of here. You can replace with this equation. So once you get the mass flow rate of BC, you can substitute into step number 2. Alright, you can see here in step number 2, which is 2m flow rate BC VBC. You can substitute in this equation. So step number 5, substitute mass flow rate of BC into step number 2. Okay, so step number 2, the equation is negative F equal to, okay, given here, alright, this term, the whole this term, okay, the whole this term, I just write it here, 2 multiply density 1.23 integrations of 29 plus y squared over 100. Remember, this is power of 2. Better we expand further, 2 times. This is still dy. Okay. Plus. And previously 2 multiply with mass flow rate BC here. You can see 2m BC plus 2m flow rate multiply with V. Mass flow rate given, we discover to be 8.2. Alright, cross the BC. And multiply with velocity. So the velocity is 30. And here minus, look at here, minus 22140. Okay, 22140. So you try to solve this. Okay, we try to solve together. Negative F equal to, you solve this, you get 2.46. Alright, integration of, okay, this one. We try to multiply. Okay, this multiply. You will get, definitely you will get, this is actually 0 to 10, yeah. 0 to 10. You will get 841 y plus, okay, plus 841 plus 0.58 y squared plus y the power of 4 over 10,000. Okay, dy. This one you solve, you will get 492 minus 22140. So you integrate this one, these 3 terms. Negative F equal to 2.46. Integrate, you will get 841 y in terms of y plus 0.58 y cubed over 3. Okay, this you try to integrate. Plus 1, the index here shall be at the bottom. Plus y, 4 plus 1 is 5 over 50,000. Okay. From 0 to and this one you solve negative 21,648. Right. So from here, negative f equal to 2.46. You solve this one, multiply with 10. 8410, okay, plus 193.33 plus 2. This one you try to substitute with 10. Substitute with 10. Minus 2164. Okay. And you solve this using calculator. Finally, you will get the drag force equal to 478.9 Newton per meter. Because the question asks, what is the drag force per meter of length? So, final answer is this way. Thank you.